Uh, good too. So maybe we'll start. So hello everyone. Thank you for joining DataCon LA 2020. Welcome to Data for Good Crack. And soon we'll be listening to using AI to build fair and equitable workplaces session. I am Ritesh Dedia, your host, and your co-host today is Thomas. We'll be moderating the chat and Q&A during the session. So I'll hand it over to Sonia and Dr. Lawrence, and you can take it from here. Thank you for being here, and thank you for presenting in Data Corner.
Thank you, Ritesh. Good afternoon, everyone. Welcome to our session. I'm Sonia Balzer, and I'm currently leading marketing efforts at R Squared. I've been working here since June of this year, and before that, I've worked at a number of different technology startups here in the San Francisco Bay Area, in the area doing B2B marketing and lead generation for over about 17 years now. Today, I'm going to be co-presenting with Dr. Lawrence Fracklin. Lawrence, introduce yourself.
Hey everyone, pleasure to be here. I'm currently CTO at R Squared. I've been focused on startups in the enterprise ML space for probably the last 8 years.
Okay. So not to talk too much about the company that we're from, but I think it's a nice segue into how we got to this presentation today and why we care about the topic of explainability in AI. Lawrence and I work for R Squared, and R Squared offers a workforce analytics platform that uses AI and natural language processing, or NLP, to mine digital communications. But our platform is a little bit different in that it goes beyond just basic productivity metrics to really understand and return actionable insights so that a company knows what's really going on with the employee experience. Our platform measures things like sentiment, collaboration, inclusivity, centrality, and many other factors that contribute to an employee's sense of well-being, as well as the behaviors and actions that they're exhibiting while they're working. So our models are scoring sentiment and human-to-human connectivity objectively without relying on employee surveys or management opinions in order to produce what we hope are unbiased, actionable insights. And so it's through the work that we do here that we've had to look more closely at the different aspects of work dynamics and culture and how those aspects should be defined in order to be fair and equitable. So in building these definitions, we understand that it's imperative to make sure we're building analysis and algorithms into our product that are not only technically or mathematically or statistically accurate, but that they're also counting every employee's contributions regardless of whether those employees are in the social majority or minority. So making sure that underrepresented groups get just as equal, fair representation as the individuals who are in the majority, which has brought us to the topic of explainability in AI and the presentation that we're doing today. Next slide. So I don't think this requires a lot of explanation. I'm sure everyone attending today can relate, because even though a lot of us have had to work from home over the past 7 months, we've all been watching the news media. We're all having some similar experiences, had to make some similar changes to our work life. And we see what's going on in personal life as well. So there's clearly a call for increased ethics and transparency going on in business. The past 7 months has placed us all in a unique time in history due to the confluence of multiple social issues that are happening all at once. So not just COVID and issues related to public health, but also other issues affecting society have bubbled up, like racism, social injustice, gender inequality, climate change, mental health, political unrest. The list is very, very long. And all of these disruptors together are leading many of us to ask if our jobs have meaning, and also asking whether or not the companies that we work for and our employers are doing enough to make things better. So there's a perfect storm right now, and organizations have an opportunity to affect some real lasting change right now after years of what a lot of people recognize has been a lot of talk with not a lot of noticeable action. A specific example of this upsurge is in the way that many companies have issued very public commitments to creating a more diverse and inclusive workplace, where employees are represented and recognized equally, regardless of their demographic or social status. DEI initiatives are becoming increasingly important for organizational leaders, even outside of the HR department, where they traditionally have resided. So then what does action leading to effective and lasting change in the area of diversity, equity, and inclusion, what does it look like? Next slide. So first, to be able to create a more, more equity and equality, you have to understand what is fair and what is fairness. So if you look it up in a dictionary, the definition of fairness is a lack of favoritism shown towards one side or another, freedom from injustice or bias, even-handedness. However, all human beings see the world differently, and we're brought up a certain way and have different beliefs and experiences that affect the way they see the world, despite even the best of intentions, right? So bias can manifest in really obvious ways, but most often it's subtle, and we may not even be aware of when it's happening. Unconscious bias, which is also known as implicit bias, is the underlying attitudes and social stereotypes about certain groups of people that individuals form outside of their own conscious awareness. But they still affect very strongly how we understand and engage with an individual person or with a group of people. And there's tons of examples of this in the workplace. There's lots of information you can find online if you work in HR. I'm sure you're familiar with all of these things, but there's things like racism, gender bias, and ageism, where you judge someone a particular way, usually negatively, based on their race or the color of their skin, their sexual identity, or their age. To counteract the negative effects of bias, there's a number of systems in place in society to make sure that bias doesn't get out of control and alter someone's life in a harmful or damaging way. Examples of these systems show up in the form of policies, regulations, and laws, most commonly, such as the ones that you see applied to financial services or employment practices. Each of these policies includes a set of anti-discriminatory protected attributes that must be factored in to protect the individuals and make sure that they're fairly considered or compared to other individuals. For example, the Equal Credit Opportunity Act prohibits credit and lending discrimination. The Equal Employment Opportunity Act is used to address employment discrimination. Attributes are organized by categories that are known or that are termed protected classes. For example, the set of protected classes under the Equal Credit Opportunity Act include age, color, marital status, sex, national origin, race, and religion. Protected classes that are included in human resources recruiting practices include race, color, religion, sexual orientation, national origin, age, and disability. So there's a lot of different factors that anybody involved in these practices has to have an understanding and a very explicit definition they understand for what all of these individual protected classes and attributes mean. Next slide. So if protected classes and official regulations are the foundation for determining and protecting what's fair and equitable treatment in society, what are the equivalent systems in place for technology that seeks to help humans make such decisions as who gets approved for a home loan, who gets approved for a credit card, who gets interviewed and hired for a job at a company, who gets admitted to a university, etc. Bias doesn't just exist in society, it also shows up in software in the form of discrimination in algorithms. A glaring example of this is the way that most AI models assume gender is binary. They see gender as being male or female. by default most times. So when considering a candidate for employment during the recruiting process, HR software usually defines a person's sex as male or female, and it disregards or rejects any other values and also any other candidates that can exist who have something different for those attributes, i.e. they identify as homosexual, transgender, or other non-binary identities that are included on their resume or that they submit in a job application. This happens because software is written by humans. It's basic common sense, and there isn't really any way to avoid it. The rules that inform a computer algorithm and the variables to be used must be coded by a human programmer. ML models are trained on human behaviors. Data used to train AI systems can hold systemic social biases. Because ML and AI require large data sets to make correlations, underrepresented populations will also be underrepresented in the data, which can just exacerbate the problem and lead to even greater data bias. And all these examples, I think the old adage of garbage in, garbage out definitely applies at a very high level. Next slide. So as AI is used to make increasingly complex and life-changing decisions, who is ensuring that these data-driven decisions are fair, equitable, and explainable? Unfortunately, today, the answer to this question is not clear, meaning that in companies building software, there's no one single person or governing body who's responsible for preventing bias in technology or even analyzing algorithm forensics. It's usually done by a group of employees as a secondary priority, or maybe it's just something that people in the company have a separate side interest. It's a hobby of theirs. If anyone is even focused on it at all, right? So just as companies looking to improve their culture on a social level, as with DEI goals and initiatives, where detecting bias and taking actions to eliminate it is now a higher priority than ever before, and where it's also understood that every manager and employee in a company is responsible for taking action. It's not just up to one person to set all the definitions of the protected classes. It's not up to any one governing body to audit what's being done. It really does take an effort on the part of everyone. By the same token, if you're involved in building AI-driven software, the onus for uncovering and correcting bias should reside with more than just one person or department. Other justifications for the movement towards preventing bias, also known as explainability, are such things as, at a super high level, just looking at basic human-to-human interaction, the more that we learn about bias in AI, the more that we learn about bias in humans, and more importantly, we learn about bias within ourselves, which can ultimately help humans make fair decisions. Explainable AI is one of the top trends in the field of machine learning today, and it's probably only going to grow in popularity. And also at the legal level, US lawmakers are proposing a bill that would require large companies to audit high-risk ML systems that involve the collection of personal information or make automated decisions. The Algorithmic Accountability Act was introduced in the House last year. Next slide. So there's definitely a call for ethics and explainability in business happening now, given recent events. Companies are feeling more responsible for providing underrepresented employees with the same treatment and opportunities as their majority counterparts. This can't be achieved without addressing implicit and explicit biases that already exist. The convergence of the demand for fairness in society and organizations and also in technology means that ML and AI will continue to become ever more central to every aspect of our lives, and the pace of adoption is only going to continue to accelerate. So if we truly want to see diversity and equality in our communities and workplaces, then we have to actively audit and correct technology to make sure it isn't biased. And for those of us who work with data or building technology, there's this growing imperative to be aware of bias and where it can show up and care about actively taking actions to prevent it. That's the first step, the awareness and knowing that it's important and having empathy for that imperative. The next step is knowing what to do about it. And then, of course, we can move on to taking the appropriate action. And it's going to take a combination of social science plus data science to make all of that a reality. Next slide. And with that, I'll turn it over to you, Lawrence.
Thanks, Sonia. So I'm going to talk a little bit now about how to go about detecting and mitigating bias. Oops, excuse me. But first, why is bias such a big problem for AI? Sonia's touched on some of these things, but when you think about it, right? Computers, shouldn't they be fair? They're logical. They don't have emotions. It's ones and zeros. The problem is that while the algorithms aren't necessarily biased, right? You can have a fair algorithm. It's still possible to have an unfair model. And that's because we basically are training those models using example data. We're pulling that example data from the world around us. And the world around us is still sadly biased, right? And therefore, it should be of little surprise that when we basically use biased example data, that the ML sort of leverages, understands, takes on those biases, and then perpetuates the problem. So you may be saying, well, Lawrence, when I train ML, I don't actually use any of those protective or sensitive attributes, right? I put those to one side. My models aren't biased, right? I'm good. And the answer is, sadly not, right? Unfortunately, even though you set aside those sensitive attributes, either because you're trying to do the right thing or because you're required to by law, a lot of the other features in your data set, even ones that are seemingly innocuous, could actually be strongly correlated with those protected features. And so the bias lives on. So what can we do about it? How do we go about tackling the problem? Well, first up, we want to detect the bias. We want to look at our data set. Is our data set biased? We want to look at our models. Are our models biased? A lot of people, once they've found the bias, they want to jump straight to bias mitigation. But I'm a strong proponent of an interim step where you spend a little time thinking about your data, explaining your data, right? Which features are the problem features? Which are the bias features? Which are the features that my model cares about? And then when you understand your models, you understand your data in more detail, you can then have a sort of strategic approach and laser-like focus to actually go about debiasing your data rather than jumping to the debiasing step too early and using more of a sort of scattershot blunderbuss approach. So first step, understand your data, right? So a lot of times when we're looking at our data, we're trying to achieve what's typically termed statistical parity or group fairness. And that's basically when we look across all of the different populations in our data, the probability of achieving a favorable outcome should be equal, right? That's what we determine, we call group fairness, right? And so we can start to look at our data, we can break it down by the different populations, and we can start to understand how close we are to achieving group fairness. A lot of people want to sort of characterize and basically measure the degree of unfairness in the data. And the term I've seen used most often is this disparate impact, where basically what you're doing is you're looking at the probability of a favorable outcome for the unprivileged or disadvantaged population and comparing that with the probability of a favorable outcome when you're part of the privileged or advantaged population. If those probabilities is equal, disparate impact is 1, we've achieved group fairness. As that metric trends towards 0, the data becomes more biased, more unfair. We can also start to look at the different features and start to understand what's correlated with what, right? We can basically generate those correlation heat maps, understand what features are actually correlated with the sensitive attributes. And a sort of fun experiment to try is basically if you take your features, can you build a model that actually predicts your protective or sensitive features, right? And if you can build a half decent model, there's definitely correlation in your data set. A lot of what we're going to talk about is this notion of group fairness, but it's also interesting to keep an eye on individual fairness and consistency. And what I mean by that is as we start to manipulate and massage the data to try and achieve group fairness, you want to understand that basically like observations achieve similar outcomes. And this is this notion of consistency or group fairness. Basically, we can take an observation, we can look at similar observations, and we define similarity using some notion of distance, right? So basically, we're computing their neighborhood. We look at the outcome for this one observation and then see how similar it is to the neighbors. If they're highly similar, it's consistent. Like events are seeing like outcomes, right? And it's something to keep an eye on. A lot of the techniques that we're going to leverage to actually try and achieve group fairness should maintain consistency, should maintain individual fairness, but you could imagine easily many different techniques whereby you could try to achieve group fairness that would violate individual fairness. It would almost be random observations being promoted to a favorable outcome, right? And that would violate individual fairness. So it is a useful metric to keep an eye on, even if you're optimizing for group fairness. We can then start to look at the models themselves, right? Basically, what is the performance, the fidelity of our models? Typically, when we think about models, we're all familiar with generating a confusion matrix, looking at recall and precision, F1 scores, but that's overall how well the model is doing. No model is perfect, there's always going to be errors, but we basically judge, yes, this is good enough, and we deploy it. But what we need to do here is we need to look at the model performance across all of the different populations, right? So we need to break out, have multiple confusion matrices in essence, and understand how the model is performing across the board. Do we have group fairness? Is an identical or at least similar proportion of all of the populations receiving favorable outcomes? There may be times in business where you can't achieve group fairness. There may actually be a correlation between the favorable outcome and some of these sensitive attributes. For instance, as a sort of a contrived example, if you're doing car insurance, right, you may want a higher proportion of young drivers to be categorized as high risk. And so there is definitely a correlation. That said, even when there's a correlation, we can still strive to make sure the model is fair and equitable for all populations. And we do this by ensuring that the error rates are consistent across. Basically, the fidelity of the model, if you will, is equal across all the populations. And you can imagine missing many of these cases, right? If you have a population, you only have a few examples for that population in your data set. The model could be performing horrible, the error rates could be terrible, significantly higher for that one population. But when you roll it up and are just looking at the confusion matrix for the model overall, that discrepancy, that disparity, that inequity is hidden. And so it's really important to actually look at how the model performs each of the populations in your data, break it out, look at the error rates, look at the ROC curves, ensure that you're actually achieving the fairness that you're striving to achieve in your models. As we talked about, I'm also a big fan of explainability, right? And this really allows us to understand why the model is doing what it's doing, right? When it makes a prediction, what features is it using? What is driving that decision? Typically, we give an observation, it makes a prediction, and that's all we know, right? If we use simple models, things like linear regression, logistic regression, decision trees, they're what are called interpretable models. And those, you can just basically look at the algorithms. You can look at the feature weights. You can understand what features are important. But most algorithms are black boxes. They're fairly inscrutable, right? And this is what explainability attempts to address. And we can do explainability at a global level. You know, what features writ large does the model care about? And we can do this at the level of the individual predictions, right? On a per observation basis, why did the model make the decision it made? There's a lot of different approaches to explainability, a lot of different toolkits out there today. Most of them tend to leverage the same sort of approach, right? Which is we can have an arbitrarily complex model, as shown on the right-hand side of the slide here, right? The decision boundary can be very convoluted, very complex. But if we have a single observation here, right, the bright red cross, if we zoom in and look at the decision surface in this localized area, it's pretty linear. And as a result, what we can then start to do is we can take an interpretable model and use it to approximate this decision surface in this localized area. We then interpret the model, we understand the relevant features. And this is what most of the explanation tools do. They take an observation, they perturb that observation, these are these other crosses and dots, generate a set of synthetic samples, push them against the predictor, it gives us the data set, we train an interpretable model on that, and then we interpret the features coming from that model. I have a quick example here. This is with respect to the Titanic data set, where it's looking at who survived and unfortunately who perished in the tragedy. We have here a single observation. It's for a male. He had a cabin, he had a second-class ticket, and there's first, second, and third-class tickets. We push this against the predictor. We can see the predictor thinks that he probably, unfortunately, didn't survive the tragedy. That typically is all the information we get from the model. But with explainability, we can actually understand why the model arrived at that conclusion, right? So here we can see that the biggest determiner was the fact that he was male. That was basically contributing most of the fact he didn't survive the tragedy. There are a bunch of features that seem to increase his chance of survival, and this is really because he had a more expensive ticket. And that matches well with what we understand about the Titanic disaster, right? Women proportionally survived more than men. And also, as often in life, the more affluent you are, the better your outcomes seem to be. We can also do some synthetic experiments here. So basically, we can say what would happen if we had the same passenger, but she was female. We can see that the chance of survival goes up significantly, and basically all of the features are pulling in the correct direction, basically increasing the chance of survival. We can use explainability not only to understand our model in more detail, why it's doing what it's doing. We can actually use it in certain cases, if you think about it, to actually provide sort of real-time operationalized safeguards against certain forms of bias, right? If we understand why the model is making the decision, we can find that certain combinations of explanatory factors are potentially biased and flag those. So there's the ability to guard against bias, guard against some of these corner cases, these sort of degenerate predictions that may come out of the corner case of your model. Also, this is increasingly required by law. If we're going to affect people's lives, if we're going to say we can or will or won't give them a loan, you need to be able to explain it rather than it just being a 1 or a 0. So we found bias. Now we need to think about fixing the bias, right? There's a variety of different ways we can actually go about that. The first may seem a little odd, but I would argue that if you can go and collect better data, better representation of the populations, less bias, more examples, more data, that's a better approach than trying to fix crappy data, right? So if this is an option, you can go out and collect more data, that's the right way to do it. And still, if it's not perfect at the end of that, you can still run through these other steps. So collect better data. We can then look if we have access to our data set, but we can't collect more, we can look at adjusting our data. We can look at adjusting our models. And then potentially, if we have a model in production that we can't change, we can't retrain, we can look at doing a little bit of post-processing on the predictions that come out of that model to make them a little bit less biased. So let's talk about some of these approaches. We can look at manipulating the data set. Typically, when we're manipulating the data set, we're doing that to try and achieve group fairness, right? So we're going to manipulate the data until this sort of unfair data that we have is group fair. We can do it with a variety of different interventions. We can manipulate the features themselves. Here, basically, what we're looking at is we're looking at features that are correlated with the protected or sensitive attributes, right? So you can see an example of this on the right-hand side. Here on the x-axis, pretend that we have a credit score or a risk score or something. Here in blue, we have the distribution for the disadvantaged population. In orange, we have the distribution for the advantaged or the privileged population. We've decided the discrepancy in those results is due to structural suppression, right? It's basically discrimination going on, and this is why we have this separation in these distributions. And so now we're going to apply algorithmic techniques, to actually try and align those and remove that correlation. We can control how much alignment we introduce, and so we can basically add a little bit of alignment, train our models, see whether we achieve the fairness requirements that we wish to impose. If we do, we're great. If we're not, we can iterate a few more times, adding additional alignment. Many models that are out there allow you to actually attach sample weights. So when you're training, you've got a set of examples, we can attach sample weights to each of those. For those algorithms, we can think about reweighting our sample such that when the disadvantaged group has a positive outcome, we're going to increase the weight of that sample. And you can see this down here on the bottom right. This is the unprivileged group. This is the x-axis, probably risk or credit score or something. When in yellow, it's a positive outcome. In blue, it's a negative outcome. We overweight positive outcomes, underweight negative outcomes. We do the opposite for the privileged group. We underweight positive outcomes. We overweight negative outcomes. The exact weights are dictated by the distributions in your data set and the fairness guarantees you wish to achieve. We can also think about manipulating the labels in the data set themselves. Typically, this is done in conjunction with a model. Basically, we train a model, we look at the decision boundary, we basically then say, all right, if there's a privileged observation that's just above the boundary and it corresponds to a positive outcome in the data set, we're going to flip that to a negative outcome. And similarly, if there's a disadvantaged group that's just below the decision threshold and it's negative in the data set, we're going to flip that to positive, right? We're going to make the data set more fair by manipulating the labels. We can also think about more wholesale transformation of the data, the features, and the labels to achieve our group fairness requirements. With all of these algorithms, we want to make sure that we basically maximize the fidelity of the data, and also we minimize any individual distortion, right? This is back to this notion of consistency I talked about. Typically for all of these interventions, we are able to maintain group ranking, right? And so individual fairness should not be adversely impacted significantly when we actually do these group fairness manipulations. We can also think about debiasing the outputs of the model. Basically, we have the model in production, it's making a prediction. We can then look at changing those. Typically, when we have a model in production, we have a single threshold, below, negative, above, positive, at least for a binary classifier. What we can do here is we can have multiple thresholds, one for each population. So if an observation relates to a male, it's subject to one threshold, to a female, a different threshold. We're going to choose those thresholds to maximize model fidelity, but also to achieve whatever specified fairness guarantee, be that group fairness or sort of equality of error rates across all of the different populations. We can think about modifying the outcome as well, right? So again, in a similar way, we have a decision boundary. We define a critical region around that. For the advantage class, if they have a positive, they're just above the threshold, we're going to flip that and say, give them a negative outcome. For the disadvantaged class, if they're just below the threshold, we're going to promote them and give them a positive outcome. And we can do that by defining critical region and doing it for everything that falls in that region, or we can take a more probabilistic approach to morph these outcomes to achieve the fairness guarantees. One thing to note is that this typically works best when you've got a limited amount of bias in your predictor. It may not always be possible to fully debias it, right? You may just not be able to get the model to behave and actually impose these fairness constraints that you wish to. Or if you do, the resultant model may be so bad that you just can't use it, right? If that's the case, you need to think about upstream interventions. We can also look at changing the algorithms. There are classes of algorithms out there now that have been enhanced to actually be bias aware. And so in addition to the normal features, you're going to pass in the sensitive attribute, and you're also going to pass in your fairness requirement, right? And that fairness constraint becomes part of an explicit cost consideration, joint optimization. This is potentially a very powerful technique. The big drawback is there's only a limited set of algorithms that have been enhanced in this way, right? And so you're limited to that. If you want to use other ones, you're going to have to look at other techniques, like using adversarial learning. This is sort of a cool way to go about the problem. Basically, if you have a model that you sort of train iteratively using sort of stochastic gradient descent, you can apply this technique. So it's applicable to a much wider range of models. Basically, we take the model, we're training it, we make predictions. We introduce an adversary who's basically trying to predict from those predictions the protected attribute, right? We then look at what the adversary can do. We use that information to update our weights, and we iterate until we get convergence. At the end of it, we should have a debiased model because the adversary should be unable to predict the sensitive attribute from our predictions. We've talked so far mainly about the example data, the training data we're using. But I do want to touch on NLP as well, because NLP is slightly different because we use so many pre-trained models in NLP. There are additional sources of bias. Typically, it comes from word embedding information and pre-trained models. So let's touch on those quickly. Everyone is probably very familiar with word embeddings, things like word to vec, glove. They're sort of cool. I mean, essentially, you take a word, you project it into a high-dimensional space, and there's lots of awesome properties of that space, like words clustered together in that space, and you can do arithmetic operations in that space. The example everyone's probably familiar with is woman is to man as queen is to king. The problem is you can also use those arithmetic operations to find some sort of darker stereotypical associations, things like man is to woman, a shopkeeper is to housewife. And unfortunately, this is not surprising, right? These word embeddings are trained on large amounts of data from the internet. internet, if you guys have ever been to the internet, it's not the world's most fair and equitable place. And so, unfortunately, these biases become sort of embedded in the word embeddings. Good news is there's a lot of research on this. A lot of people have come up with techniques to debias word embeddings. It's something you can do yourself. And people are now publishing and making available debiased embeddings. The one that comes to mind is ConceptNet. I also want to talk about, transfer learning and pre-trained models, things like BERT and GPT, right? Everyone's probably heard of these. Basically, these are the models from the Googles and the Facebooks. They take a lot of GPU time, vast amounts of internet data, and they train these models so that they sort of quote unquote understand language. And they've really been transformational, I would argue, in NLP, right? They're very, very powerful. You can use the pre-trained models directly, or you can apply a small amount of example data and fine-tune them to your specific task. Very powerful, though, but the problem is potentially very biased, as you might expect coming from the internet, right? They've potentially internalized all of those biases. StereoSet from MIT sort of drills into this and allows you to probe and understand some of these biases. This one is with respect to stereotypes associated with British people. As you can probably tell from my accent, I'm from the UK. So I thought this one would be interesting. Basically what they're doing here is they're showing it a first sentence and they're leveraging BERT's next sentence prediction abilities. Show it sentence one, and then you say, given these other sentences, which ones are most likely to follow that first sentence? Which sentences are related in essence, right? And you can see here, the first sentence is the man from Britain moved to New York. And then we've got two subsequent sentences that on the surface should be identical. They're both just talking about food and beverage choices. But BERT believes, very strongly that one is more likely to follow the first sentence than the other. And this is because of the stereotypes it's learned about British people. For the record, I do like coffee. The good news is that...
just like we are left with 5 more minutes.
Yep. Thanks, sir.
Yeah, sure.
So basically, the good news is there are a variety of different techniques out there for debiasing pre-trained models without sacrificing accuracy. So just coming to my final slides now. Again, when you're thinking about NLP and BERT, explainability is your friend. You can use it to actually understand what words in a sentence BERT is using, or any pre-trained model or any NLP model to actually make its prediction. So here we have a sentiment model. The statement we're looking at is, he's an extremely unpleasant man. It correctly believes this is highly likely to be negative. But what's interesting is we can make sure that it's not doing a sort of biased prediction, right? We can see the words that it's actually picking up. Why does it believe this is negative? It's because of the presence of unpleasant. It's because of this modifier, extremely. He and man is in there, but that's not unexpected, right? You'd want it to, this is focused on human behavior, not my sentiments around pot plants or wallpaper. We can flip it around and make it about a lady. And it's good to see that the probabilities are the same. It doesn't appear biased. And equally, it's not picking out any terms here, right? It's not the fact that she was a lady or British or anything like that that's causing it to think this statement was negative. It's these words that you would expect. So again, we can use it to understand our models. We can use it even in operationalized scenarios to provide some safeguards. If we're starting to see some weird explanations come out, we can flag those, right? And so it does provide additional safeguards in operationalized solutions. Some resources, hopefully when we share the slides, the hyperlinks come through. And so just to conclude here in the dying seconds of the presentation, AI is biased, will be biased. It's biased due to the fact we live in a biased world and there's biased training data. I would argue that if we as data scientists are doing data science projects and we are impacting the lives of other human beings, responsible AI is the critical consideration, right? We're impacting people's lives, their opportunities, their outcomes here. We need to do it right. But debiasing cannot be an afterthought. We need a comprehensive debiasing strategy. Fairness through an awareness is not sufficient. Understand your data, right? Really drill into it. Good news is there's a lot of open source techniques and a lot of open source toolkits to help you explain, reduce, and remove the bias. And then also, I think the biggest part is really, as Sonia mentioned, just governance around this, right? Strategy, oversight. It shouldn't be the Wild West. We shouldn't just be deploying random models into production. We're impacting people's lives here, right? There needs to be a risk assessment. What's the upside? What's the downside? What could go wrong? Where's the bias? And also, we need a diverse set of opinions. Everyone needs a seat at the table. It can't just be some white dude who's deciding what's biased and what's not, right? We need that diverse oversight, right? But we can do better. The AI community is starting to wake up to this problem. We're starting to develop the techniques and the technologies to help with this. And so, I think the future is bright. And with that, I will conclude. I think we're up on the time, right?
Yeah, and thanks a lot, Lawrence and Sonia. That was a great presentation, actually. I have been working in data for a long time, and there are a lot of learning for me as well, how to look at the data from a bias perspective. I've been never think from that perspective, and I really appreciate you and all the attendees joining this session. And if you have any questions, because we are not left with Q&A time, you can ask any questions to Sonia and Lawrence on the MOVA app, and hopefully they will respond back to us. Yeah, and again, thank you very much and appreciate your time.
Thank you. Thanks to everyone who attended. I hope
Thank you, everyone.
Useful.
Yeah, thanks. Have a great day.
Thanks. Bye, everyone.